All right, let's jump right into this explainer. Today, we're literally popping the hood to see exactly how a backend manages data and scales up to millions of users without just completely buckling. If you've ever find yourself wondering about the actual architecture powering those high-traffic apps we use every day, well, you are in the exact right place. We're going to trace the entire journey, starting from basic local system calls all the way up to global cloud load distribution.
So here's our roadmap for today. We'll be looking at 1. The node file system, 2. Building an HTTP server, 3. The cloud and scaling, and 4. Routing with Express. Let's get into it.
Seriously, think about this for a second. We interact with these brilliantly seamless apps every single day, right? You open up a social network, you request to see a profile, maybe process a quick transaction. But how does the code behind the scenes actually parse your request, talk to the database, and stream that data right back to your screen without crashing under the weight of thousands of other people doing this exact same thing? Well, it takes a beautifully orchestrated stack. To build these massive systems, developers rely heavily on a magical little concept called abstraction. It is an incredibly powerful principle. It's kind of like hiding the complex, oily, complicated engine of a vehicle so you can just focus on, actually driving the car. We don't have to sit there and write raw C++ or interact directly with the machine's kernel to talk to the operating system. Instead, we simply use APIs and prepackaged modules that execute all those low-level instructions for us. That frees us up to just focus on the actual business logic of whatever app we're building.
Okay, Section 1, the node file system.
So the first big challenge developers run into is needing to manipulate the native file system on a computer, but doing it without writing tedious, low-level machine code. Node bridges this gap perfectly by giving us the fs, or file system module. This fs module is basically a brilliant wrapper around those complex C++ functions, giving your server-side JavaScript the absolute superpower to talk directly to the OS. By just importing this core module, you instantly get an elegant way to breeze through file operations. You can create, append, rename, copy, and delete files with literally just a few lines of code.
Let's put this into a real-world scenario. Say you're building a server and you needed to keep a log of network errors. You'd use fs.writeFile to create that log file when the server first boots up. Now, as traffic hits and minor bugs inevitably pop up, you definitely don't want to overwrite that file, so you use fs.appendFile to just continuously add new error data, maybe tossing in a \n to make sure the logs stay neatly separated on new lines. Later, if you want to archive it, fs.rename easily updates the file name with a timestamp, and to clear out an old log, just use fs.unlink to delete that specific file. But hey, a quick word of caution here. Literally every seasoned developer has a horror story about fs.rm. If you trigger a remove command with a recursive flag in the wrong folder, you could accidentally wipe out critical production folders in the absolute blink of an eye. So, with great abstraction comes great responsibility.
Moving on to Section 2, building an HTTP server.
All right, so this brings us to client-server architecture. Once you have control over the local files, you really need a way to share that data over a network, right? This entire setup works a lot like a continuous, highly orchestrated handshake. The client, which could be your web browser or a mobile app, kicks things off by requesting specific information via a URL. Then the server, which is our node backend in this case, intercepts that request, reads the details, does whatever logic is needed, and sends back the correct data. It's just an infinitely repeating loop. Request, response, all communicating strictly over HTTP protocols.
To actually make this handshake happen locally while you're building the app, we bind our node process to a specific network port, like port 3000. You can think of a port basically like a dedicated door on your computer. Your machine has thousands of background processes running at any given second. By explicitly telling our node server, hey, listen on port 3000, we ensure that when HTTP traffic comes knocking at localhost 3000, it knows exactly which application to talk to. It just guarantees our app intercepts the payload instead of the connection just dropping into the void.
Which leads us to Section 3, the cloud and scaling.
Okay, so now we have a fully functional local server. It's sending out responses, it works beautifully during testing, but imagine your app suddenly goes viral overnight. If 3 million concurrent users unexpectedly try to hit port 3000 on your local laptop, no way. It is going to crash instantly. A standard machine simply doesn't have the available RAM, the network bandwidth, or the processing power to juggle millions of connections all at the exact same time. The server will hit a massive bottleneck and just drop everything.
To actually survive a massive traffic spike like that, you have to move from your local, fixed hardware up to a distributed cloud environment. So instead of relying on your physical laptop, you deploy your backend using a service like an Amazon Web Services EC2 instance. The absolute brilliance of this shift is that it unlocks elastic computing. Unlike your static laptop, an EC2 instance lives in an environment where it can dynamically scale. If your users suddenly jump from 10,000 to 1,000,000, your architecture can instantly grab more RAM and allocate extra CPU cores to absorb the immense shock of that traffic, completely avoiding any downtime. It's a total game changer.
And, this quote brilliantly illustrates what an EC2 instance actually is. People say, deploying an EC2 instance in the cloud, and it sounds super abstract and honestly kind of intimidating. But at the end of the day, it is literally just a rented computer sitting somewhere near Delhi or Virginia in a massive climate-controlled data center without a monitor attached to it. That's it. It's basically a robust operating system running 24/7 with a dedicated IP address that you securely log into from your house to host your code. Architecturally, it is exactly the same as your local machine. It's just infinitely more powerful.
Okay, last part. Section 4, Routing with Express.
So your infrastructure is robust now. You've got incredible hardware redundancy sitting in the cloud. But as your application scales up, managing thousands of different HTTP endpoints manually, that becomes a total nightmare. Relying solely on raw node HTTP is incredibly clunky. You'd be forced to manually parse URL strings, manually extract headers, and write so much repetitive code just to send back a basic response. So to get around this, developers introduced another amazing layer of abstraction, the Express framework. Express sits neatly right on top of that native HTTP module and completely streamlines things like error handling and, most critically, routing, turning them into elegant, simple functions.
Notice how a routing table completely organizes all this potential chaos. When someone types in a domain name, the internet resolves that human-readable name down to your specific AWS server's IP address, and the traffic arrives at your application. But the route, that specific path at the very end of the URL like /about or /profile, is what tells your Express application exactly what to do. Express cleanly reads that route and instantly directs the user's request to the precise block of logic needed to fetch that specific data.
So, pulling this whole shebang together, we can now map out the complete lifecycle of a modern backend request. A user starts it off by clicking to see their profile. The domain name system instantly translates that domain into an IP address, routing the traffic right to your highly scalable cloud server. Your Express app intercepts that connection, sees the /profile route, and uses those native asynchronous modules to query your database. It grabs the exact data payload for that specific user, slaps on the proper HTTP status codes, and streams it right back across the network so it can be beautifully displayed on their screen.
And there you have it. We've scaled all the way from running basic system calls on a tiny local text file to engineering a globally distributed cloud architecture that can handle millions of concurrent connections. But as you digest all of this, here's the next really fascinating question you should be asking yourself. With an absolute avalanche of requests constantly hitting your robust cloud server to read and write user data, how are you going to architect the database behind it so that it doesn't become the ultimate bottleneck? Think about your data structure, and we will catch you in the next explainer.